So, I'm going to give a talk today about reimagining system engineering through adoption of ART methods. Right? So before we get there, though, I want to give you a little bit of background about myself, about the department, and about the research and the methodology that we use. So I am the director, I guess, of the Imagines Lab. So that's located over in the Industrial and System Engineering and Engineering Management Department. So if you've heard of ISEAM, that's us. That's me, myself, Dr. Colopy. That's also Dr. Petniga, Dr. Thomas, Dr. Messimer, Dr. Swain, and Dr. Golston. Right? The four that make up the system engineering group are us four right here. So myself, Petniga, Thomas, and Colopy. And our mission statement, our goal to educate you guys, is the system engineering program at UAH allows theoretically grounded practitioners capable of advancing and utilizing rigorous mathematical methods. Right? So we care about rigor, we care about making sure things are right, not just ad hoc, to rapidly produce novel and dependable systems within predictable budgets, and we're focusing on aerospace and defense systems. Right? Since we're in Huntsville, that's going to be our focus. So the team at the Imagines Lab, so this is the majority of them. Specifically, we have 4 graduate students and 3 undergraduate students currently in the lab. Most of them are in this picture along with their friends and significant others. And the philosophy of the lab is to pursue creative and novel research in the foundations of system engineering to enable a reimagining of systems engineering. And that's where the Imagines Lab name comes from, reimagining of systems engineering. So we have 2 main research focuses. So the first focus is on decision making in systems engineering. So we're looking at reducing inconsistencies when the systems engineers or any engineer make a decision. So making sure that we have consistent decisions all the way through the design process, both laterally across the organization as well as vertically through the organization. The other research focus that we have is looking at the art of systems engineering. So if you're at a university, you're taking all these gen ed courses, how do they relate to systems engineering? Right? It's not something that you just pass off after your second year in and then move to the mathematics of engineering. Well, how can we incorporate those into systems engineering, and how does that better us as engineers? So these are our 2 main research areas that we're looking at. So what's wrong? Why do we care about the art of systems engineering? So an easy diagram to explain this is as complexity goes up, the development time has also been increasing. And for the aerospace engineering field, 8 to 12% increase in cost per year is also occurring. This is unsustainable. Right? We're having big issues here. There's stories about how in 30 years we'll only be able to afford 1 aircraft and it'll be shared amongst the 4 different military branches, right? So there's issues that are going on that we need to address. So there's some indicators that we're having problems both in industry and academia. So in industry, we're losing about $200 million per day due to cost and time overruns, due to project cancellations. This is an issue. To put that amount of money on a scale of $200 million per day, the Afghanistan war costs $45 billion per year. That's roughly 200 million-ish per day, right? That's a big issue. We need to deal with that. We can't just let that fly by. In academia, we have all of these approaches, and they're mostly rule of thumbs in systems engineering. So if you've seen any of these, this is an engineering V diagram. Basically, you have your main system at the top. You decompose them through requirements, and you build it back up. Right? We have spiral diagrams. We have the waterfall method. Right? We have an approach that looks at structure, behavior, and requirements all tied together. None of these are actually founded on solid theory, and that's worrisome. Right? In mechanical engineering, we can go in and we can see thermodynamics, and we can drill down to the theory behind that. Right? Control theory, we can drill down to it. We can get to fluid dynamics, right? We can get down to the theories that build up that discipline. Systems engineering, not so much. Right? So that's an issue. So we're looking at arts and other methods, other areas out there to feed the theories that we need to build system engineering on. So what specifically do we do in the lab? What methodologies do we use? So we look at the tools of agent-based modeling and game theory and everything that's incorporated in that to get a better understanding of the systems engineering approach. Specifically, what I want to explain to you guys today is game theory. Right? Since we don't have a course yet in game theory for you guys, I'm going to explain it now, and then hopefully when you go to grad school here, I'll teach you again in engineering econ in a little bit more depth. So what is a game? So a game is an interaction among two or more people where each player or person's actions affect the other person. Right? So think of any board game. Generally, there's an interaction of players there. Right? That's a game. Think about when you're designing something. You're interacting with somebody. That's a game. Right? Your behaviors are impacting someone else. Game theory is just the mathematics of examining those games. Okay? So that's game theory in a nutshell. So most people, when they hear about game theory, hear about the prisoner's dilemma. So let's talk about that. So in the prisoner's dilemma, there's two captured people. So we can say Sansa, I think, and Reek. Right. It's been a while. I'm pretty excited about April, but I haven't rewatched the episodes yet. So these two prisoners are brought in accused of treason, right? But there's not enough proof to put them in jail just yet. The guards are then interrogating each of them individually, right? And they're greedy individuals. They only care about themselves, right? They've abandoned hope for the other person multiple seasons ago. So if the one person snitches, then that snitch goes free and the other person ends up getting 3 years in jail. If they both snitch on each other, they both get 2 years in jail. And if they both stay silent, then they get brought up on a lesser charge and they only go to jail for 1 year. And then the question, do you want to play a game, is would you do? Would you snitch or would you stay silent? Right? Now, a lot of people will look at this and say, well, I'm going to stay silent because 1 year is pretty darn good, right? Other options are I can go to jail for 2 years, I could go to jail for 3 years. There's a possibility of going to jail for 0, right? But if I stay silent, at least I know 1 is what I'm going to get, right? Assuming the other person stays silent. So what we can do is use a payoff matrix to actually show numerically what's going on in this game. So here we have myself, we have the accomplice, and we have different outcomes between looking at different actions. So here we have snitch and snitch would be in the top left. We have I snitch and the other person stays silent in the bottom left, and so on. And these are the number of years you would go to jail. So if we both stay silent, I would go to jail for 1 year. If I snitch and the other person stays silent, I go to jail for 0 years. Right? So you can represent it like this. So still the question is, should I stay silent or should I snitch? This doesn't tell us. What we have to do is look at the interactions with the other player. Right? Without those interactions, this means nothing. So we can make a payoff matrix with both players now represented. And here we have each of their outcomes. And now a negative number is bad, so you're trying to maximize, right? So negative years in jail, more or less. So we have a row player and we have a column player. And we can see that if both people confess, if both people snitch, they both go to jail for 2 years. If both players stay silent, they both go to jail for 1 year. If the row player stays silent and the other player snitches, the row player goes to jail for 3 years, and the person who stays silent goes to jail for 0. Right? So the second number here is the column player, and the first number is the row player. Now what we can do is use something called Nash equilibrium, and we'll get into that in just a second. But what it does is that you show your best reply to the other person's best reply. We can go down here and look at, okay, if I know for sure that the row player is going to confess, what is it better for me to do? Confess and get -2, or stay silent and get -3? -2 is better. So what I can do is block that in. So if I know the other guy's doing confess, I should do confess. And it's the same for the column player. The column player is doing confess. The row player is choosing between -2 and -3. -2 is better. So I go and circle that one. For withhold, if I know the row player is doing withhold, then the column player is choosing between 0 if I confess and -1 if I withhold. Obviously 0 is better, so I go ahead and block that in. Where those cross, where it's both circles and circles and squares here, is what we call a Nash equilibrium. Each player's strategy is a best reply to the other player's best reply strategy. In a different phrasing of that, a player can't do better by unilaterally changing their decision. So if I'm here at confess, confess, it doesn't make sense for the row player to go withhold because he'll get -3. And same thing for the column player. It doesn't make sense for them to go from -2 to -3 by changing from confess to withhold. If I'm down here at withhold, withhold, it makes sense for the row player to switch to confess because all of a sudden he goes from -1 to 0. If we're then at confess, withhold, it makes sense for the column player to switch because he goes from -3 to -2. So not only are you stuck on that, but you end up at that point regardless of wherever else you are. So both best outcome if both players withhold, but player's best interest is to confess, right, over here. But you get a better outcome if you were to withhold. So here's a little video on Dilbert trying to use Prisoner's Dilemma. Okay, so Dilbert understood the problem of Prisoner's Dilemma, but he didn't understand the solution, right? Both Alice and Chinook there knew that it's best for them to confess, to snitch out the other person, in this case, Dilbert. So Nash equilibrium comes from John Nash in the 1950s. You might know John Nash from this picture, right? And this is the real John Nash, right? So just like we said before, no player has incentive to deviate unilaterally from their strategy at a Nash equilibrium. And a pair of strategies is a Nash equilibrium in a game if and only if each strategy is a best reply to the other. Right? So we get stuck at that point. It doesn't make sense for anyone else to move off. We can do this for pretty big games. Right? So here we have a 6x5 game where the column player has 5 different alternatives, actions that they can take, and the row player has 6 different alternatives or actions they can take. And we can go through and circle everything, right? So if we know that the column player is doing Y2, it makes sense for the row player to do these 49s because they want to maximize their value. It doesn't make sense to do 0.2 or 0 associated with the X1 and the X2. So you go through with that mindset, with that process, and you can end up at a Nash equilibrium, which would be over here at X3, Y3. So it doesn't make sense for the column player to switch. They're at 0.6 right now. They would get 0.51, 0.19, 0.6, 0.6, right, which are the same. And then for the row player, it doesn't make sense for them to switch because it'd be 0, 0.2, 0.25, right? 0.4 is the best. So that's the solution to the game. If you play this repeatedly over and over and over again, the players should figure out that this is their best move. So there's also something called a mixed strategy Nash equilibrium. In most of the board games that you guys will play out there, you'll end up with a mixed strategy Nash equilibrium. If there was a pure strategy Nash equilibrium, which is what we call this, it'd be a pretty boring game, right? Because you know exactly what people are going to do. Tic-tac-toe can become this pure strategy Nash equilibrium, right? The Nash equilibrium of tic-tac-toe is tie-tie, right? If you play optimally, you'll always tie. For mixed strategies, though, this is when you have a probability distribution across different alternatives. So think rock, paper, scissors. Right? If you always threw rock, that'd be pretty obvious to your opponent, and they're going to capitalize on that. Right? So it makes sense to switch it up. That's what mixed strategy does, is it switches up. It makes randomness within your movements. The famous game that you would learn in game theory is called matching pennies. Essentially, you have one player has a penny. They're going to show heads or tails, and they're going to hide it. And the other player is going to guess whether they're going to show heads or tails. So one player, the one with the penny, would win if the guesser is wrong, right? So if I'm showing heads and the guesser says heads, I would get no points and the guesser would get 10 points. If I showed heads and the guesser said tails, I would win. Right? So I'm trying to make the other person get it wrong, the other person's trying to guess correctly. A whole lot of math. We get to a solution. It turns out 50% of the time you want to do heads, 50% of the time you want to do tails. Right? All of this is essentially using expected utilities, and you can bring in risk preferences, which is graduate level stuff. Unless there's some decision analysis elements in there. Maybe you'll hear about it in your decision analysis class. So what good is all of that, right? There's mathematics to examine games. There's games and systems engineering by designers working together. Us as systems engineers, as project managers, possibly in the future, if I can talk you guys into it, is what we would use as mechanism design. So essentially what we're doing is setting the rules of the game in order for outcomes that we desire to occur. Right? So if we want certain people to play rock and paper, I can rig the game in order to get them to do that. I can do things like give them incentives. So maybe I give them $1. You play rock and I'll give you $1. Right? Or I can give them future contracts or profit shares if we're talking about the real world. I can change their alternatives, so I can hide alternatives. So maybe I don't let them know about papers or scissors. Right? I only have them do rock. And I can change their beliefs. So I can maybe give them test data that shows that, hey, if you play rock, you're more than likely to win against this individual, this other player. And I can do simulation runs in order to build up those beliefs as well. A few other quick games in game theory. Some classics. One is chicken, right? So Rebel Without a Cause, you have two cars coming at each other. There's a very narrow road. Both of them aren't going to fit. So one of them's got to pull over to the shoulder. Right? The payoffs here, if both cars pull over, you get +2. If you're the only one out of the two to pull over, you get 0 because you feel, demasculated if you're a man, I guess. I don't know. You don't feel good about yourself, right? If you have to pull over on the side and let the other person through. If only one pulls over and if you're the only one to drive straight, you get +3. You feel like you won the battle. And if both drive straight, you crash it against each other and you get -1. And you can do this with Nash equilibriums, with game theory, right? So here we see that it's best to do speed up if the other person's going to slow down, and it's best to go slow if the other person's going to speed up. So you get these competing Nash equilibriums now, which is really becoming a challenge. There's not a single Nash equilibrium. There's not a single solution of the game. You might have one player figure out this Nash equilibrium and the other player figure out that Nash equilibrium, right? Which might not be good if you both choose to speed up, right? If you both choose to go straight. Another example is the prime location. So you got an ice cream cart on the beach, right? You're going to sell ice cream on the beach. You have people from 0 to 10, and we will just say these are miles, right? If I'm going out there on the beach, I want to be close to as many people as I can, so I'm going to set up right in the middle of the shop, right? That way, the person that's farthest away only has to go 5 miles. Well, that's a horrible example. Let's say 500 feet, right? We'll put these in hundreds of feet. Now what happens is Papa Pops comes in, and he sets up shop at 800 feet, right? And I'm sitting over here at 500 feet. The people are going to go to the person that's closest, right? So Papa Pops is going to get everyone from 6.5 and over, and I'm going to get everyone from 6.5 and to the left over here, right? Now, what should I do? If I know he's at 800 feet, I should move my cart over here to 799 feet. And then I get everyone to the left of that, right? And that's exactly what you would do. Papa Pops is going to figure that out. He's going to move slightly to my left and get everyone to the left. And we're going to keep doing this over and over and over again. And eventually we're going to end up both pretty much at 500. Where we're splitting the population. I get the left, Papa Pops gets the right. Right? So you can think, okay, that's a pretty easy example. But why would that happen in the real world? Pull up a Google Maps, search for gas stations, search for fast food. You'll see them clustering. Right? That's the prime location problem in action. Right? It's best to be near each other. It's best to be near the competition because then you're reducing the distance that people have to go to. You can also see this in elections. Right? So in the primaries, Democrats and Republicans are typically in the middle of their base, right? Typically in the middle of their base, and then come the general election, they'll shift into the center. Right? That way they reduce the space. If one party stayed in the middle of theirs, the other party shifted over to the center, they would get part of the base of the other group. Right? And You're trying to secure your base and trying to get the independents that are in the middle, traditionally. Okay, those are the methods we use, right? So we use game theory in order to explore many of the problems in our lab. But now let's talk about the art methods and where we can pull from the art to improve systems engineering. So the first is knowledge. Oh, sorry, why art first? I believe we can improve system engineering by identifying approaches from the arts that aid in understanding and in performing systems engineering and infuse those approaches into SE. So that's kind of our mantra in the lab. And here are some opportunities. So first, knowledge. So the storage of knowledge is pretty complicated in systems engineering. We're working with pretty complex systems. So here we have the Saturn V. A pretty complex system designed in the 50s and the 60s. Right? Worrisome fact, a lot of those people who worked on the project are retiring, right, or passing away. And we're losing a lot of knowledge associated with these large systems that were built back then. Right? So why was that design, that bolt chosen, right, when it doesn't seem like an optimal design? How do we store the contextual information, what the person was experiencing at the time they made that decision? How can we store that information in order to enable us to recreate that decision-making process? That's a big challenge right now, and we don't have a good way of doing it. Luckily on campus, we have a really good library and a really good archive, and they have lots of information about NASA projects, right? But it's overwhelming how much information they have. And to weed through that and to figure out what's the good stuff and what's the bad is hard. We need a better way to catalog it. Right? Archivists, thankfully, have methods and approaches to conserve and preserve information. And us as systems engineers need to take that knowledge and use it to capture preferences, beliefs, alternatives that are needed to reconstruct the decision. So that's one area we're exploring. Another area is in preferences. So understanding stakeholder preferences, how can the art help us do that? So we see, it's hard to read, but we have government, communities, suppliers, investors, employees, customers. We have all of these people that are interacting with our products, with our systems, and we need to understand the needs and the desires of each of these individuals in order to give everyone the best system. So the challenge here is how do we capture stakeholder preferences to enable decisions consistent with that of the stakeholder? How can we make decisions so the stakeholder will be happy at the end of the day? And that stakeholder might be the CEO of the company. It might be the American public, whoever that stakeholder is. A possible answer is the arts, and it's found in theater. So here, actors must analyze scripts in order to develop a character, understanding the character's desires and being able to portray those desires. So they need to get into the shoes of that individual. They need to understand how that person makes a decision, which is exactly what we as systems engineers are trying to do. How would that stakeholder make this decision? So what we're doing over the summer is an art and systems engineering boot camp. So it's going to be a 3-day event. We're going to do character development and creativity from the arts to train the engineers. The engineers are going to train the theater practitioners using design processes. So we're going to have an exchange of knowledge. If you're interested, get a hold of me. That's going to be in the summer. If you want to participate, we're looking for students now. Framing is another issue. So here we have these large systems that we deal with, these complex systems, a Saturn V, a Boeing 737, 8 MAX, whatever it might be. It's very complicated to show these detailed issues within the system to stakeholders. Right? How do I go to my boss and say, I made this decision because of this reason? Right? When the system, and this is a picture of the internet, right? And you're a dot somewhere in that network, right? How do you explain all the interconnections and all the interactions that are going on in this system? So what art could we use there? Right? So the issue is how do we present and communicate information about the system to other stakeholders to enable efficient and effective engineering and improved system performance? Right now, this is one of the best ways that we have to convey information in systems engineering. Good luck with that. This is model-based systems engineering. This is a view from model-based systems engineering where you have boxes and you have relationships that are occurring. It's extremely difficult to communicate through that software right now. right? You have to be an expert in that software to really understand what's going on. Not really possible when you have stakeholders from marketing, from business, from all other disciplines. So we can look at film as a possible art that can help us in systems engineering. Directors have approaches and methods to convey important information to the viewer and draw emotion and engagement. So this is a clip from San Andreas. This is right after so spoiler, this is right after an earthquake hits Los Angeles. Notice all the little details that are going to be in this scene, this quick 10-second or so scene, that conveys what's going on in Los Angeles right after the earthquake. So we notice the airport's shut down. It was violent enough to cause explosions and fire. You see cracks in the baseball field, right, indicating major infrastructure issues. We see destruction in the streets. On a boat is The Rock and his companion, and he notices quite quickly an issue that arises. And within these 5 seconds, you can probably figure out what's going on now, right? The wall of water is about to hit the city. 30 seconds captures it pretty quickly. Apollo 13, spoiler, there's an accident in space. He goes to stir the oxygen tanks. Very quickly, it's communicated to the audience that something happens with the tanks, and now there's errors and chaos in the ship. So the question then is, what can we do in systems engineering? What can we pull from film in order to better communicate our problems in systems engineering? Training is where game theory really shines. So in systems engineering, we have these long life cycle phases. You think up of a design, you build requirements, you analyze, and you do the actual designing. Eventually, you get to implementation. Looks pretty easy on this little flowchart. That could take 20, 30 years, right? That's a nightmare for systems engineering because you're not redoing the tasks repetitively, right? You're not getting experience by doing the conceptual design over and over and over again for similar systems. Right? You might do it once every maybe 5 years if a new system comes down the line. And the other issue is once you do your conceptual design, you have to wait that 20 or 30 years to see what happened. Did you make a good decision? Right? So what can we do here? The challenge is, how can engineers learn from their mistakes when it may take decades to overcome, to determine the outcomes? Here we have the F-22 Raptor, 24 years from initial requirements to entering service. That is quite a long time to wait to see, does my decision, was that a good decision to make? So we have a possible answer in game design. So learning games that are meant to train you, to educate you, can be used, and the designers of those games have methods and approaches to train certain skills in players. So here I randomly picked 4 games from my collection. So Sheriff of Nottingham, essentially what you're doing is interacting with others and you're trying to sneak goods past the Sheriff of Nottingham, right? So you're essentially lying about what's in your bags of goods. And essentially what you're doing there is bribing the sheriff to let you pass. You're training people on how to use incentives, right? How do I get that person to let me buy without looking in my bag of goods? In operation, you're talking about coordination. That's an actual physical trait. Pandemic is a cooperative game. You're trying to rid the world of diseases. It deals with probabilities. There's these cards that occur, and you have a general idea of what's in the deck. So you know, okay, there's a 1 in 5 chance of this card coming up. Power grid is auctioning off certain blocks in certain electricity areas, and you're teaching people how to deal with auctions, right? How do I outbid someone else? Finally, we're looking at surrogates for systems engineering. And the question here is, does systems engineering approaches work, right? Now, they might produce something, but but are they producing the thing that you intended to do with that approach? So how can we evaluate systems engineering approaches? So going back to an earlier slide, we have all of these approaches: V diagrams, value-driven design, MDO, agile. Do they actually work? And that's a big question in systems engineering. There's no theory right now that says in systems engineering these approaches will produce the most efficient or the most effective design. Right? And that's worrisome. What are the theories? What is the evidence of these approaches? You might use an approach and it might get you a product. Do you have 30 other approaches with 30 other products to compare to? You don't. It takes 20 or 30 years to produce these products. You simply don't have that information. So we're looking out in the real world for actual surrogates so we can say, okay, this is a surrogate of a systems engineering process or a system engineering product that we would eventually get. Can we then use our approaches to see, does it produce a good design? So one possible area is in theater, and we could use theater productions since they have lots of people interacting with them. There's a final product at the end of the day that you can measure. You can get an idea of was it a good production or a bad production. Right? And we could possibly use theater productions or other surrogates to validate some approaches. It doesn't provide the theory, but it provides some evidence. Something to point to say, this approach worked better for these 20 theater productions than this other approach did for these other 20 or 30 theater productions. So why would theater make sense to do here? Right? So it has some desired research characteristics. There's lots of playhouses. Basically every town has a playhouse, so that's awesome. Availability is high. The cost is decently low, in the thousands to produce a show. And the duration is pretty low. We're talking months instead of decades. So that's all good. Things that are related to systems engineering that are good, there's a hierarchy of individuals. You have actors, directors, marketing, everyone working together to produce something. You have many disciplines within that organization, right? So you have marketing, you have music, you have lighting and engineering. There's life cycles involved with theater, just like there's life cycles involved with systems engineering. There's phases and there's scripts. And there's a final product that you can measure. All of these are good, right? These are things that are involved in systems engineering, and these are things that are also in systems engineering but are the opposite. There's low availability to explore different approaches. Their costs are in millions and billions, and the duration is decades. So we're trying to capture system engineering attributes, but have the bad ones be turned to things that we can manipulate easily. At the same time, the duration of decades might be a major flaw in systems engineering, right? That might cause the surrogate not to be good. That's what we're researching right now. Is theater and other arts a good surrogate for systems engineering? This is a comparison of just milestones between systems engineering and theater. They relate very highly, right? So preliminary design review, we do a feasible concept and we select it. We're doing blocking and stumbling through theaters. There's lots of relationships there that have been identified. The student Julia Palma is currently working on this right now. Okay, and the list goes on. So I have an undergraduate student right now, Amanda Banks, who's looking at fashion templates. We're also looking at abstraction and elaboration. When do you see the bowl here? I can probably figure it out here. Right? Yeah, that's a bowl, right? Maybe some people need to get up to here. Maybe some can figure it out down here, right? When you're presenting information in systems engineering, how much detail do you need to give to make a decision, right? How much elaboration do you have to do to enable the communication of information to another stakeholder? We're exploring that topic as well. So why art? So I believe we can improve systems engineering by identifying approaches from the arts that aid in understanding and performing system engineering and infuse those approaches into systems engineering. And in general, I want you guys to think about, well, how can I, as I'm going through my studies, incorporate all of these general education classes that I'm taking into the field that I'm looking at? Right? How can I better myself as a person, and how can I better the field by incorporating those other disciplines? Those disciplines that might seem crazy, it might seem far off, and might be out of reach. How can I pull it in and help my discipline and help my studies? That's all I got.